Welcome to Matrix Tech Talk. Today, once again, we have Peter Gliwa, the CEO of Gliwa Embedded System. Peter, welcome to Matrix once more.
Thank you very much.
So this episode, we're going to talk about some technical details of timing. So Peter is the founder and CEO of Gliwa Embedded Systems, where the main product is a timing relevant product. So Peter, I will let you introduce your company, your products a little bit, and tell us a little bit about your products. What does your company do and your product does?
Okay, so the starting point some 16 years ago was timing problems actually, and the great need to be able to look into what's really going on in the embedded software on the real system, so inside the automotive ECU. And therefore we started with instrumentation-based tracing. So we hook onto the operating system in a way that we capture task activations, starts, terminations, interrupts, beginnings, ends, and we trace them into a trace buffer on the target. So it's a purely software-based solution with all the advantages and disadvantages that gives you. This gives you. So it's on the upside you have the complete independence of any hardware interfaces, the availability or anything. So we don't need any debug ports to be available, no Nexus, no JTAG, nothing. So we have several gearbox ECUs where the ECU itself is surrounded by oil inside the gearbox. There's no way you can connect anything to it, a hardware trace or anything, no, nothing. Talking about the RX, for example, this approach doesn't need the emulation device. We're not even making use of the on-chip tracing infrastructure. It's really a pure software-based solution. So that's the upside. On the downside, you have an impact on the system, of course. Tracing comes with some overhead, and so it costs something. It costs execution time, and the trace buffer costs RAM. You need some RAM. You need to spend some RAM for the trace buffer. So. And here we spend a lot of effort in getting the overhead, getting the impact really down to the absolute minimum. And I mean, we still keep replacing in-house solutions, and what we always do is we leave the in-house solution active, integrate T1, integrate our solution, and in the end, with T1, measure the overhead of the previous in-house solution, and that always gives us a nice feeling. So far, there's to state some figures, the overhead on a typical chassis ECU or engine management is something between 0.1 and maximum really 0.5% for tracing, so less than 1%.
Less than 1%.
Yeah, absolutely. So we do, yeah. On top of that, we have on-target timing analysis. That means maybe one step back. So this tracing provides you nice traces you can download from your ECU and visualize on the PC. Visualize using the T1 host software, where you can see like what was going on. It's a snapshot trace where you see the sequence of execution of tasks and interrupts. Others refer to it as a Gantt chart, for example. So that's the T1 scope component. Scope like in oscilloscope, because that's pretty much what it is, oscilloscope for your software. Then another component is the T1 cont, which is the component that gets executed on the target and performs timing analysis there. So without even having any PC connected, it permanently monitors the timing parameters and checks it, for example, against given timing constraints. So you can put your timing requirements you found and formulated in an early phase of your project. You can have those checked really in the car. And therefore we actually had the target software certified according to ISO 26262, ASIL D, in 2016. So more and more projects actually not only use our tools as some tracing or timing measurement infrastructure, but it becomes part of the safety concept of the software. So it becomes really part of the software, supervises the timing at runtime, and if any timing constraints are violated, you have your error buffer entry, DTC entry. You can withdraw functionality, switch to a safe state, and so forth. On top of that, there is some fancy technology that allows you to modify the instrumentation at runtime. So whenever I show that, I kind of tell the whoever's watching, okay, now you're going to see some magic. We read in all the symbols from the ELF file and just select any symbol and have it instrumented while the system is executing. Or open source code from the software, just mark a fraction, mark a few lines in the source code and say, okay, what's the core execution time of that? And then we instrument the software at runtime. So that's the magic bit in the tool. And the 4 years ago, I think, or 5 years ago, we, on top of the whole timing topic, as one of the resource-related aspects, we added stack analysis. So there's a new component, T1 stack, well, new, 4 or 5 years old, which is the regular stack analysis. So static code analysis, you disassemble the executable. From that, you build up the call tree, calculate the stack consumption per function, and put everything together in a nice visualization. And last December, we extended that to memory analysis. So one component called T1 Excess Predictor. So it predicts which kind of memory excesses you will see in the software when being executed. So again, static code analysis. So everything is statically analyzed. And then you know which memory regions, which variables are accessed. And one use case is, well, optimization. Another use case is a feature we called offline MPU, because this is really what it is. Once you know which memory locations your software accesses at which points in time, you can compare that to your MPU configuration. And then you will see, look here, we will potentially run into access violation here at this point in time. And these access violations, they're very costly to track down in the field once the software got into the car or even into the hill. And so we developed that for more than a year with one big tier 1 in Germany, and they're very happy. They say they don't see any more memory violation exceptions in the field.
Fascinating. So is your product T1, or the memory or stack tracing software, is basically for the target? Once the software is flashed to the target, you can measure, you can instrument the code and you can measure them, or even in the car or in the hill, as you've mentioned. Now, if you look at the process, the V model, and if you really have a major timing problem, and if you detect it once the code is flashed in the ECU, isn't it a bit too late? Or, I mean, not too late, isn't it a bit late? Is there any way with your tool or with anything to detect this problem a bit earlier in the development phase? During modeling, maybe?
Yes. I mean, the static code analysis based components, T1 stack and access predictor, there you don't need to flash it to the software. This is really pure static analysis. But coming back to your question regarding, once timing problems occur on the target, isn't it too late? The answer is, again, yes and no. So our product doesn't include anything like scheduling simulation or static scheduling analysis. So we focus really, let's say, on the bottom of the V cycle and on the right side. We don't have anything for the left side, for the early phase. There are several other timing tools available to which we have interfaces. So we can provide input to them. for example, the minimum, maximum core execution times, or even the whole configuration. Once T1 is integrated, we have a view on the setup, which tasks exist, and so forth, and we can generate, for example, an Incon project file, just to name one of them. And and actually, I strongly recommend the use of these tools because, most importantly, any user of scheduling simulation will start to think about timing early in the process. And this alone is very, very valuable, because you're not kind of put things together, grab some old project and put a balcony here and extend it there a little bit, and that's your, well, I wouldn't call that timing concept. So once you start with scheduling analysis, scheduling simulation, you start thinking about what is it actually that I want, and that's a very good aspect. However, this is not enough. So during our last sessions, I've been mentioning avionics, and they have a very strong focus on stopping there. So they do model-based timing analysis, and that's fine. And then they say, well, we have really had our worst-case execution time static code analysis, and we have this and that. So actually, we don't need to look at the real system anymore. We don't need to do tracing, and we don't trust it anyway, and so forth. Well, so we have seen projects where, or we were involved in projects where or the model-based approach said, green, everything's fine, but the system crashed. And crash and avionics is something, two words you don't want to put in the same sentence, actually. So, in our, let's say, timing workshops we do for OEMs, for tier ones all around the world, there's one picture in the slide set. I can't show it now, but I can explain it. So, on the one side you see a brain. On the other side you see some embedded hardware. And then above the brain and above the embedded hardware you see some, let's say, curve, right? And the one above the brain goes like up, and the other one goes like this. Now the message is, well, you have something on your mind, but reality behaves differently. There's a gap between your model, and when you're thinking about something, it already is a model. It's not reality, it's an image of reality, so it's a model. So even every thought you have is a model. Yeah. When you think something works like this, it's not reality, it's what you think it is. So, and there's quite a gap in between, and then what I show is, how do you get from here to there? And it's a long way. First of all, you transfer your idea of, your functionality into some maybe high-level model-based software, MATLAB, Simulink, or ASCII, or whatever. So that's the first transfer you make. And then you have a code generator. Then you have the compiler, you have the assembler, you have the linker, you have the locator, you flash that thing onto your target. So it's a really long way down, and with every step things can go wrong. So how can you come up, insanely, with the idea of not having to check the final result with the initial idea, with the initial model?
It's almost like Chinese whisper.
Yeah, it is. To some extent, it really is. And you know what? Really funny thing, from that avionics project, I had one quote. After we finally found that there was a gap, but, and we could identify it and visualize it and explain it. Once we looked using tracing technology, we looked at the real world. The responsible project leader, you know what he said? He said, yeah, the gap between theory and the real world is bigger in the real world than it is in theory.
Love that.
Even though they know there's a gap, the gap is bigger than you think it is.
Yeah.
And that really underlines also our experience we had when optimizing our own software. As I mentioned before, we have really, really super highly experienced embedded software developers. And they get surprised again and again and again. They think, that's the outcome of something, and then they measure. They look at the real numbers, and they see surprises. And with increasing complexity, the number of surprises also really dramatically increases. I mean, talking about static code analysis, it's hardly impossible to have a real worst case number in a multi-core system. I mean, I'm talking about the theoretical worst case in a real multi-core system, including interrupts and everything, will be so big that if you design your software according to that real theoretical worst case, at least in automotive, you can't afford it. It's not possible.
Fascinating. So, automotive industry is about to face the biggest disruption, unprecedented disruption in the history of automotive industry. There are 3 disruptions that I think is going to change everything: connected vehicles, electrification of vehicles, and autonomous vehicles. So with that definitely comes safety challenges and new challenges, security challenges, and many other. Let's focus on safety a little bit, yeah? So with your tools, what I really like about your product is that these are really practical products. You're really, we're not in the theory or not on the model level, we're really at the implementation level. So let's say freedom of interference, one safety issue that we always want to deal with at the ECU level. Does your product give any kind of support for implementing such thing or demonstrating freedom of interference?
Yes, it provides, for example, the measurement of maximum core execution time. So it's measurement based. It's not no theoretical number, but the fact that you can actually put it in the car and collect all the numbers, store the figures in non-volatile memory, gives you a huge test basis. And actually there's a funny story where we in one project measured core execution time which was greater than a statically analyzed core execution time. Oh, guess what happened? The customer was puzzled completely, and then we talked to the company providing the static code analysis, and at the beginning they just didn't want to talk to us. They just said, "No, hey, are you questioning maths or what?" And we say, "Yeah, okay, we'll double check the numbers." And we say, in the end, no, actually, I'm pretty sure that these figures are correct, and they're higher than the worst case you stated. In the end, well, they investigated and found that the memory setup they used for the static code analysis was wrong. So the tool wasn't wrong; it was the configuration of the tool was wrong. But again, a big gap between the real world and the theory. This customer, they've been supervising their software, they've been checking their software for 1.5 years based on these theoretical numbers, which were all wrong by a factor of, I think it was 1.3 or 1.4 too low. And so that was quite interesting. But coming back to your question, so freedom of interference, I mean, that's something that you have to somehow prove when you certify your software according to ISO 26262. Even if you don't certify it, if you develop it according to ISO 26262, what we mostly see, then you have to show the freedom of interference. And one way of doing that, straightforward, come up with a safe timing setup, maybe which you analyzed using static scheduling analysis, scheduling simulation, and then make sure that all the execution times keep within their boundaries, and that's a very good way of showing that you have a safe and sound timing. You mentioned the really new aspects of automotive, one of them being electrification, so electric vehicles. In this context, I have a nice story to tell. So we've been involved in electric vehicles since 2003. So right from the beginning of the company, we worked for. I can say that it's been released in several talks. So we've been supervising the timing of all the electric vehicles from Daimler and the fuel cell as well as the battery-driven ones. And I remember, I don't know how many years ago that is, but we were talking about timing requirements, and there's, for example, the external watchdog, right? On every ECU you have, or at least if it's to some level safety relevant, you have an external watchdog that keeps checking whether the processor is still alive. On the processor itself, in the background, typically you execute all kind of checking algorithms. You check some of the peripherals, you check the memory, you check the actual calculation unit, and so forth. And this is done in some sort of round trip, right? So you perform all the checks, and now you have to complete that such a round within which time? Well, that's the question. What's the timing requirement regarding the completion of that cycle? And for engine management, the answer is, well, let's assume something goes wrong in the software because we have some alpha radiation, the processor breaks and gives wrong results. Maybe a maximum torque queue request. That's for engine management, the worst case. You have a maximum torque queue request. Just imagine you have a zebra crossing. You're waiting for pedestrians to cross the road, and all of a sudden your car makes a sudden move. And they found that an acceptable kind of movement of the car to keep it in the acceptable limits, this maximum torque queue request is 200 milliseconds for combustion engines. So they performed all the analysis, and it boiled down to 200 milliseconds during which you have to detect the failure, the wrong maximum torque queue request. Now, electrification. Let's talk about electric motors. You don't have a clutch, a slow clutch. You don't have this motor with combustion engine that needs to speed up to develop power. An electric motor will give you the maximum torque queue right out from the beginning. So it's a different situation. And Daimler actually, they did their own video on that. They had a diesel car and the electrical vehicle, and then they applied 200 milliseconds maximum torque queue request on both of these vehicles. And the diesel engine, the diesel car went like, slow movement and immediately stopped, slowed down. And the electrical car just shot off, and it was so obvious. Put that to a zebra crossing, and you're going to kill somebody. Yeah. So timing, electrification. That was just one very, very obvious example where you need to come up with different constraints. For example, in the end, they boiled it down to 70 milliseconds request now, during which they have to identify a software failure. And these are kind of things, they have great impacts. The whole software design, with the very fast ADC conversions, you have very fast interrupts now you need to handle. So on a low level, many things are very, very different.
And that's gonna impact the autonomous vehicle manufacturing too, because when you have electric cars, the detection of object will have to be faster than the diesel car, don't you think?
Yeah, talking about complexity, very obviously complexities are very increasing in automotive. I think it's not enough to say it's just increasing. I feel like we're adding a new dimension like every 2 years. So the complexity really grows exponentially, and that's really dramatic. So I've been watching some of the previous videos, and there you came up with the question of, what's the impact for engineers, and they will work on higher levels, I think. So we also keep adding levels, like 40 years ago.
Yet another abstraction layer.
Yeah, abstraction layer, absolutely. So 40 years ago you had assembly language, then high-level languages like C, and then C++, then model-based languages, code generation. So we keep adding levels, but still at some point you have to get down to the low levels if something goes wrong. And not only if something goes wrong, because I think that's too late, you have to permanently monitor also the low level if everything is still fine. And I mean, that's the idea of timing measurement, of tracing. And of course, you want to do that in an automated way. You don't want to have somebody sit there and, clicking the mouse all the time. That's what you want to do in nightly tests or CI fashion. And you can do it. You can do it even in a way that doesn't use up additional hill time, because that's very expensive, of course. So you can parallelize your timing measurements, your timing supervision, your timing verification with the existing functional tests. That's no problem. You can do that. So
fascinating. What do you think of, because of these technologies, adaptive AutoSAR is going to come. We have classic AutoSAR. Tell us a little bit of your tool. How does your tool work with the classic AutoSAR, and what would be the difference when adaptive AutoSAR will come? How will it, fit in? And what are you doing in order to be prepared for adaptive AutoSAR?
So when multicore was introduced to the automotive market a couple of years ago, we faced a very similar situation. So up to that point in time, everybody was developing single-core software, and they were very familiar with that. And all of a sudden, we had this multi-core stuff. Do I have different ELF files? Do I have a single ELF file? How do I develop multi-core software? How about the timing? How can all of a sudden, protecting data by disabling interrupts doesn't work anymore. It's not sufficient. You have to use. You have to have semaphores, spin locks, these kind of things. But then on the other hand, they cost very much, and so there were very, very many question marks. And and at that point in time, we made sure that T1 was ready very early in the process. Actually, we were at that point in time a customer to Infineon, for example, even before the Aurix came out, to get the ecosystem around the Aurix ready to use. So wasn't closely related to our timing analysis. That was just debugging debuggers, debugging compilers. But in this context, we made sure that our timing analysis product T1 is ready whenever the Aurix is presented to the open market. So it was there from the very beginning. And it functioned like a bridge for many software developers who knew our product, visualizing their single-core software. And now it showed them their multi-core software, all the things that go wrong, all the synchronization problems, all the data access problems, and so forth. They had their synchronized traces across all the cores, and that helped them a lot. So that kind of bridge from single-core to multi-core is what we're currently seeing, the same situation from multi-core to heterogeneous, many-core systems, which you need for autonomous driving. So, and there we're trying to repeat the story again, so that our tool is kind of the bridge to the new world. One, you're asking for what steps we take in order to build this bridge, and one of these steps is the fourth poster we presented just a few weeks ago. So I know you know our posters. So it's the fourth poster. It's like that shape, that size. these posters are focusing on really technical aspects. So we're not talking about products. We're talking about, the first one was in automotive timing in general. The second one multi-core. Third one ISO 26262, and the new one is on adaptive platform. Focusing on adaptive platform. It's got a comparison CPAP, so classical platform, adaptive platform, and it mainly explains how could you address timing in an adaptive platform project. For example, when you use the deterministic client, how where do all the timing parameters from your past, how do they fit into the new world? Where can you see your delta time? Where can you see your core execution time, for example? So one aspect I don't hear very often is, to some extent, I think autonomous driving is also a hype. I mean, look at the car in 5 or 6 years' time. Open it up, look inside. How many ECUs will you see? Yes, there will be this huge big number cruncher, maybe 2 of them, 2 boxes. But all the other ECUs, they're not going to go away.
They're not going to go away.
You're going to have 50, 60, 70 of these other ECUs in there.
Yeah.
So that's what I mean. So it's everybody is focusing on autonomous driving, but please don't forget that for many, many more years, we will be dealing with single core, with multi-core, and all the stuff we've been dealing with over the past years.
And definitely your the ECU that you have for your steering HMI, your cluster instrument HMI, these smaller ECUs are not gonna go away, because it absolutely doesn't make any sense with this small little computation. You go to this big number cruncher and come back. It makes absolutely no sense. You have to do them locally.
Safety aspects, for example.
Safety aspects. Yeah. So Peter, because of this disruptive technologies, technological advancements taking off so fast exponentially, in the coming 5, 10, 15 years, what do you think would be the most positive thing that you will see?
Well, maybe 2 positive aspects. One is the chance to reduce casualties on the road.
Absolutely.
So people always see the risks. When I say people, I mean the not necessarily developers, but in general, if you read the newspapers, many people just talk about the risks. But hey, we've gone beyond that point many years ago, right? So when ABS or ESP was introduced, right, then at that point in time, you handed over the control to some electronic device, and if that breaks, the right wheels, you're just going to fly off the road. So that's a risk, yeah. You have a software error, front and rear wheel on the right side, they break, you fly off. But maybe it sometimes happens, but the number of lives saved by braking correctly in a difficult situation is so much greater, and nobody questions that. So I think these little boxes, they are lifesavers, and they increasingly will be. Right, so you won't, in just a few years' time, you won't have those lorries, when there's a traffic queue, they shoot into the end of it and killing many people. That's not going to happen in 20 years. That will be history. So I think that's the most positive effect.
I totally agree. We focus too much on the very, very low probable negatives when it comes to autonomous vehicle, where we don't see that this is going to be a game changer in terms of the casualties on the street.
Yeah, perfect. I mean, I just can underline every word you said. Absolutely. And the second aspect, maybe that's more personal one. So I ride my bike a lot, and I just can't wait to see that point in time where I don't have to breathe in all the exhausts. So that's going to be fun. Already it became so much better. So I do remember what it was like 20 years ago. Waiting with other cars at the red light, and you just go, hold it, I'm going to go in a minute because but so that's changed already, but this will improve.
Due to the electrification?
Yes, I think so.
I love that. So less casualties, saving more lives, and cleaner environment. Love that, Peter.
Absolutely.
Thank you so much for joining. It was my pleasure to have you here.
Thank you very much, Hassan, for inviting me. Thank you.
Thanks. Thank you so much for watching. If you have liked this episode, please feel free to write comments. You can also ask questions to our guests directly by writing us to podcast@matrix.de. See you in the next episode. In this podcast show, we bring in the industry leaders and experts in the automotive domain to share their experiences along their journey. The mission of our podcast is to start a dialogue that will allow us to understand the development of automotive industry and where the automotive industry is going. You can ask questions to our guests directly. Just send us an email to podcast@matrix.de. We'll schedule a call with you during the recording and you'll be part of our show. Make sure you subscribe so that you don't miss any new episodes. Please share this video to help others get enlightened as well, and that would mean a great deal to us. See you in the next episode.